threads, threading, and thread repair. Take 3. Screw terminology. Now, not all of these are as important, so we're going to go over the ones that are important for us. So righty-tighty, lefty-loosey, that one is just denoting that there's right-handed thread and left-handed threads. Most vehicles, most fasteners on cars today will be a right-handed thread. That means as you turn it clockwise, it screws in. There are some applications where there will be a reverse thread. And I know in some cam timing systems, like on the Ford 4-liter, some of those cam bolts are actually left-handed thread. Back in the 60s, half of the vehicle, one side of the vehicle would have the wheel studs would be left-handed thread, and the other side would be right-handed thread. And the idea was that, you know, if those wheels are rotating counterclockwise, then the lug nuts, they'll definitely want to back off. And we know that's not true, but it was the 60s. An interesting note is that you can actually screw a left-handed thread into a right-handed thread hole. It will be tight all the way, but it will screw in. I've seen it done. So, you know, that's that. The grading of the bolt, if it's a standard bolt, it'll have dashes on the top of the head or no dashes. So if it has none or some, you're going to take however many there are on there and add 2, and that'll tell you the grade of the bolt. For metrics, it will be embossed on the head of the bolt literally. So if it's a grade 8.8, it'll say 8.8 on the head of the bolt. The other things that I want to look at, don't worry so much about the root. Length of engagement, we'll talk about that. The overall length, that is how long the bolt is, including the head of the bolt. And then the rest of them, other than the class of fit, we'll talk about. The rest of them we don't need too much on. So a closer view of this, of a bolt. So with our bolts, the first thing I want to look at is something called the major diameter. The major diameter is, you know, the threaded section. How big is the threaded section when you measure across it? And we're going to be measuring from crest to crest. So this side, we've got this crest, and then we're going to be measuring over to these crests right here. Now these points on the thread are easy to contact with a pair of calipers. So I'm going to do a quick measurement over here on this bolt and see what it zeroes out at 0. And if we open this thing up and close it off, and we see we got 7.81. Now this is the actual major diameter of the bolt, but this bolt is an 8mm bolt. So we have something called nominal, okay? Dang it. Let me erase that real quick. Erase. There we go. Let me try to write this down again. Nominal. N-O-M-I-N-A-L. So the nominal bolt size is what size of bolt, what size is written on the box that you got the bolt out of. Or they say this is an 8mm thread when they use an 8mm tap. Well, this is an 8mm bolt, but that is not the actual size of the bolt. So if we need to determine the size of the bolt, you can use calipers, but just understand when you measure that, that measurement is going to be less than what the nominal size is of the bolt. So that's nominal. The other things that we have to worry about are the pitch of the bolt. To be able to measure the thread pitch, it's best to have thread pitch gauges, and that'll tell you, you know, what the pitch is of the bolt. There's a diameter that's easy to measure with a pair of calipers. The pitch, not so much. Now, if it's a standard pitch, it will be threads per inch. If it's a metric pitch, it will be, you know, the distance from one crest to the next. So trying to measure something that's only in millimeters in length when you have some that are 1.0 and 1.25 millimeters, 0.25 millimeters is not a big difference when you're trying to use calipers, so it's best to use thread pitch gauges. The other thing about threads, and this is something that's good to know if you work on many different brands, the British brand especially, is the 60 degrees. So The angle between this thread and this thread over here, this is a full 60-degree sweep, so half of it's 30. And 60 degrees is the common thread angle from metric and standard. So it kind of tells you why some metric bolts will screw into some standard holes, kind of. And if you ever work on any old British stuff, they don't use 60 degrees, they use 55 degrees for some reason. They just decided to do it different. All right, so on to the next one. So length of engagement. So this concept of length of engagement is, you know, how many threads does the bolt screw into in the hole? If it's a nut, the length of a nut is going to be at least the diameter of the bolt. And the idea is that those threads that are engaged will be stronger than the bolt, because they don't want the threads to be the weaker link, because that would be hard to control. You know, the bolt, yeah, we can give a bolt a tensile strength, you know, give it a certain amount of pull strength before it snaps or deforms, but the threads, we need to make sure that they're stronger than the bolt. So length of engagement is important. So the basic engineering states that the fastening system failure should occur at the point of the bolt. Not in the hole, not on the threads, but the bolt needs to fail, because that's what they can definitely test the easiest. So this is the concept that we can use for thread repair. Let's say somebody's working on, I don't know, an engine, and you have to go over there and fix it, and they've messed up the hole where, you know, this top two threads or top one thread, those are damaged and not usable. Well, if you can measure from here down to the bottom of the hole to figure out how long the length of engagement is on that bolt, you know, and if you're at least the diameter of the bolt, or maybe even 1.5 the diameter, then you just say to yourself, well, if I just fix this top part, maybe, you know, grind this part out, or, you know, cut back this thread so that it doesn't impede the use of the other threads, then you're good to go. So you have the proper length of engagement, instead of trying to blow out the whole hole with a drill bit and retap it. Okay, so bolt torque. Bolt torque comes from an engineering aspect. It's not so much how or what the bolt is tightening. Is it a head gasket, or is it a front cover, or is it a seat belt? All these things really don't have much play in how much torque is applied to a bolt to get it to the proper tightness. Bolt torque comes from the diameter of the bolt and the length of the bolt, the thread of the bolt, and in some other respects it's going to be what the bolt screws into, what's the material of the thread that it goes into. So we can look at this chart over here, and if we take a look at, let's say, the 7/16 bolt. Okay, that 7/16 bolt, and they're not saying this is a carburetor bolt or an engine mount bolt, they're just saying it's a 7/16 bolt. We have a 14 threads per inch and 20 threads per inch, and we see that we have two different torque values for these things, and these two different torque values are, you know, based on you know, if it's 14 threads or 20 threads, so it depends on how many threads per inch or what's the pitch of the bolt. The next thing that we look at is this two-column group where we have dry and lubricated. And if we look at that same bolt, the 7/16 14, we've got 99 foot-pounds of torque and then 74 foot-pounds of torque for lubricated. Now the reason that is because a lot of our force, a lot of our energy in torquing does not actually go into tightening the bolt. So if we look over here on this side, we see that 35% of the torque goes into just trying to overcome the friction of the threads. And we can see that because if it's dry and no lubricant, we're at 100 foot-pounds, but if we add some lubricant, we're then at 75 foot-pounds. So that's a 70 or 25% reduction. Now the other part of the equation is the underhead friction. So if we take a look over here on the table, when I'm talking about underhead friction is we take this bolt here, this is a 6mm by 1.0 bolt. That underhead friction is whatever the head of this bolt is tightening down against with this face right here. They're saying 55% of our torque force goes into tightening that bolt. 55% of that is going into overcoming the friction of the head of the bolt pressing down against whatever it's tightening. And then that last 10% that's left over, that goes into stretching the bolt. Now, the only way a bolt will stay tight without any thread locking compound is if that bolt is stretched. And the way it's going to stretch is right about here is where this bolt it engages in the threaded hole right here down. That bolt is going to stretch right through this section here. It doesn't need to be a lot of stretch. It just needs to maintain some stretch to it to keep this thing tight, because if we just tighten it down and it had no tension against it, there'd be nothing holding this head down against the material and maintaining that high friction so that the bolt doesn't back out. So just keep that in mind. A lot of our torque energy goes into just overcoming friction. Now, because of this, they've come up with, I say they, but engineers have come up with a very precise method of torquing, and that's called torque to yield. And in torque to yield bolts, usually what that is going to be, you're going to tighten it to some foot-pounds, and let's say you're tightening it to 10 foot-pounds, then you back it off a turn. So the first tightening is actually seating everything in place. And then you're going to back the bolt off to let it relax. And then you're going to tighten it again to, say, a higher foot-pounds. Let's say you take it up to 20 foot-pounds. But remember, only 10% of that torque went into stretching the bolt. The last step is going to be tightening the bolt to a certain number of degrees. So if you have a 2mm thread pitch bolt and they say, okay, tighten it to 15 foot-pounds and then tighten it 90 degrees, well, if that thread pitch is 2 millimeters, if you're tightening it and everything's already compressed, you're then going to be stretching the bolt by some factor of thread pitch. So half a turn of a 2mm thread pitch is going to be 0.5 millimeters. Half a turn is 1 millimeter. 2 turns is going to be a 2 millimeter stretch on the bolt. So the bolt is being stretched as you tighten it, and that's torque to yield. And in most cases, torque to yield bolts are a one-time use bolt. Okay. Class of fit, this is something relative to taps. If you purchase taps, in most cases taps are going to be considered a 2A tap, and the die are going to be a 2B tap. So if you could imagine like cheap furniture, maybe like outside furniture or whatever, if you've ever assembled that, you know how when you put the bolts in the holes, they're really loose, but they tighten down and they do the job. Well, those are going to be considered a 1 class or a 1A and a 1B. Most of the bolts that we work with are going to be a 2A, 2B. And of course 3B, that's going to be a very tight fitting bolt. But just understand that if you're buying used taps, you want to make sure that you look at them and they don't say 1A on them or 3A, because you're just going to make too tight or too loose of a thread. So make sure 2 is the one you want. Okay. So determining thread dimensions, like I said earlier about the nominal compared to the actual major diameter, you're going to measure it with calipers. So let's go over here and take a look at a couple more. So this one right here is a 6mm bolt, and so we've got 5.85. So if we were to clamp down on this and we saw 5.85, we would say to ourselves, well, that's a 6mm bolt because I'm just under 6 millimeters. And then about this one's bigger than either of the other two, and we're now at 9.86. And that 9.86 is indicating that this is a 10mm thread. The next step that we need to do is determine the pitch. So using a thread pitch gauge like this here, okay, so I have on it the 1.0 thread pitch gauge, and I'm just going to go between bolts. You're not going to do it like this, but I'm just going to show you with the one gauge out. And we see that there we go. We see that this thread pitch gauge does not engage into that thread on the bolt. So that one there, that's a 1.25 thread. This one is also the same, but if I bring out this 6 by 1.0, we see that thread pitch gauge falls in and it locks in perfectly. So we know that this is a 6 by 1.0 thread bolt. The overall length of this bolt, overall length is not that important because this is overall length. If I go from here to here, from head to stern, that's our overall length. And while that's not super important, it's sometimes how bolts are classified if you're buying them from a hardware store. So we want to try to consider that. But really the more important thing is, what is the length of the bolt, okay, under the head. So this is underhead length, and this one looks like it's going to be a 30 millimeter underhead length. And it's just a measurement. I can't get to the right gauging point on this one, but this is a 30 millimeter bolt. The length of threading is another thing too, because if we've got, let's say this bolt needs to go through an unthreaded section, and then our threaded section starts down here, this bolt would be fine. But what if that threaded section was, say, this long? That would tend to cause an issue, because that unthreaded section is, it's not going to thread down into the threaded hole. So instead of using a bolt like this, we then would have to use a bolt like this, to where it's actually got the threading all the way up to under the head. So that's another factor that we need to consider. And that's the thread length. And then of course the head diameter. And we see that these two bolts here, while they're the same thread pitch, same thread diameter, they do have two different head diameters, and maybe this one screws into a softer material than this one does, or maybe it's a clearance issue where if this is the bolt you're replacing, you can't use that one because the head of that bolt is too big. Over on the standard side, or the inside empirical, and for both of them, on the grading, metric, it's going to say literally on the bolt. So we have up here, this is an 8.8 grade, that's a 10.9. I believe this is a 12.9, I just can't see it right now. You want to replace it with the same grade or one step higher. You don't ever want to go down in grade. Never go down, but you can go up one. Because you're going to at least guarantee that that bolt is going to hold exactly what it held before, strength-wise, or slightly better. You don't want to step up too far, because then you start getting into maybe clamping it too much and causing distortion. Same thing for thread diameters on the Unified. You can measure the diameter of the bolt with a pair of calipers, and remember, it's going to be slightly under the nominal. So if it's a 3/8 bolt, you're going to measure it. It's probably going to measure, instead of 0.375, it will probably measure about probably 0.368, 367, somewhere around there. The pitch, same thing there. You're just going to have a second set of thread pitch gauges. And then, of course, all the same stuff on the thread length, thread engagement, and stuff like that. Thread types, different types of threads out there. Really the ones that we worry about the most is that if we're working on something standard, inch-based, there's UNC and UNF. UNC is coarse, so if we have a 1/4 inch diameter bolt, we have a UNC, which would mean it's 20 threads per inch. Or a UNF, which would be 28 threads per inch. So we have a coarse thread and a fine thread, and that's just indicating how many threads per inch, and these are standard numbers for the Unified ones. But if you're working on old stuff, old American stuff, that's what you run into. Metric, there's not really any standards for metric. There are common ones for metrics. So if you were talking about a 6 millimeter, it's going to be 6 by 1.0, and that's what they would consider a common or a standard for metrics, but it's still 6 by 1.0. That's not to say that there's not a 6 by 0.8 or a 6 by 1.25. It's just the common one, most common one, was 6 by 1.0. Then we get into pipe thread. So pipe thread is for sealing some cavity or sealing some gallery. So if you can imagine, there's probably oil or something down here, because these are both, this is a pipe thread here. It has a sealing component. So over here on the right, we've got a straight thread, and this might just be a metric straight thread, but this guy has a sealing washer right there, okay? That sealing washer is the sealing component. So the oil that's underneath here, it will make it through the threads, I guarantee that. But once it gets up to the sealing washer, it stops. Okay, so the oil stops and it can't seep out. Now notice over here on the tapered thread, two things. There's no sealing component like the washer over here or an O-ring, and the head of the bolt is not reaching the surface of the threaded hole there. Now the reason is it's not supposed to. You never tighten a tapered thread until the hex bottoms out. Tapered threads don't stop turning. What they do is they deform the thread. So the harder material, which is sometimes going to be the male thread, is going to screw into a softer material. So we might have a steel bolt or steel plug screwed into aluminum, and that aluminum is going to be displaced, because if we keep screwing this in, this larger section will eventually get into this narrower section, and that swedging the material, that metal to metal contact, is what is going to seal the tapered thread, tapered threaded plugs. Over here in the video, or on the table, we've got I've got a tapered tap, and this tapered tap it's a standard one, and I'm not so much measuring anything, but what I want you to see is that when I put these calipers into it, I can still wiggle this back and forth, because where I'm measuring it at now, out here, is much larger than here. On these taps, like this one is what's called a quarter 18 NPT, or just a quarter NPT, is going to be a 1/4 inch of taper along the length of this, and that's the size. It's not anything about the diameter, because if you think about it, if we let this thing taper down all the way out, it would go down to 0, or back this way, it would go much larger than a 1/4. So the 1/4 is the amount of taper on it. There are quarters, there's 1/8 inch, 3/8, 1/2 inch, 3/4, all different taps for NPT. And now they're going to be bigger the bigger fraction it is, but it's not so much anything about the diameter of the tap, it is the taper on the tap. Alright, so there's that. Alright, so thread geometry, we said this already, just going to hit it again. Metric and unified are both 60 degrees, okay? The major diameter is going to be less than the nominal, and that's on both of them. The thread pitch is measured on metric from crest to crest in millimeters, and thread pitch on the unified is how many threads will fit within an inch. Okay? How threads are manufactured, I got three videos here for this. So external threading, for threading, say for a bolt, is they've got a method called single point cutting, and then thread die. You can use a die to cut the threads, and then roll forming. Internal, we have tapping, thread forming, thread milling, in process threading, and that means the hole isn't threaded but the bolt will thread it. And then EDM, which is one we won't need to hit on. Alright, so threading. So this video here is going to show a couple of things, different ways of threading. So the first one it's going to start with is with a traditional hand tap, and that's going to be similar to this one here. So there's going to be a hand tap. The next one it's going to show is a spiral point tap. And then the last one is the spiral flute tap. Actually, not the last one. There's another one that I forgot to get out, which is called a thread forming tap. But we have a hand tap, then we have the spiral point, and then we have the spiral flute. So let me find our spot in this video. All right, so this first one, this one here is tapping a hole, and if we watch, or if we look at this, so if we look at this this video, what's happening are these leading edges of the flutes are actually cutting the hole. They're cutting the material out for the thread. And those, because these things are basically, flat faced, it's just curling inside the flute, and you see these little curls, and they'll actually curl up bigger depending on the material, and they can bind up inside these flutes, but these chips are falling down to the bottom of the hole ideally. All right, so there's that one. The next style is going to be more for automation, because you notice on this one here, instead of having small individual chips falling to the bottom, we have the cutting edges. Notice the cutting edge on this is angled, okay? And these chips are falling down, or they're curling down and then going down into the bottom of the hole, and that's good for automation. So it goes down through the hole. And then this one here is kind of a reverse of the previous one. So earlier, the cutting angles were angled like this. Now these are angled like this. And what's happening is that those chips are actually curling, and they actually curl and come up out of the hole, again for automation. Now you can hand tap with these, but they tend to be more difficult because they don't provide a good centering. So this last one here, I'm going to stop it whenever they get to, actually I'm going to stop it now. Notice there's no chips, there's no pieces falling down here, but what's actually happening is this tap is exceptionally hard and very smooth, and what it's doing is it's actually forming, kind of like Play-Doh, it's forming the material into the shape of the thread. All right, so this is the benefit of this one. The second benefit is that the grain structure is actually following the thread. On the earlier one, the grain structure is being cut out. So this is thread forming. It's a really good way of threading. It also provides no chipping, so there's no material to dispose of. All right, so let's go to the next one. All right, this is single point threading. What this is the shaft that's been machined to a specific outside diameter, and see there's no threads on it right now. And the machine that it's on is a lathe, and it's timed, so the lathe is capable of maintaining that position over and over and over again. And you see that he cut it and then created a small curl. Now the end of this cutting piece is actually machined into 60 degrees. And that's the shape of the thread. So we'll watch a little bit, and then I'll skip ahead to where we have a more developed thread. Okay? So we'll come out here. Notice the thread is developing more. We still have a pretty flat crest on the top. And he's going to keep machining. Now this process is pretty slow, but you know, gets the job done until we're pretty much there to fully form threads. Okay, on to the next one. So this one right here is thread rolling, and this one uses, I think it's a 75 horsepower electric motor to drive everything. This one is similar to the thread forming tap, except this is going to be forming the threads on a shaft. So let me go ahead and skip ahead in this one to where we see it actually forming, and I'll describe some of the components. So they're installing the shaft. This shaft is about 4 inches in diameter, maybe about 100 millimeters. So you see what he's grasping up here is the shaft that's going to be threaded. Now these are the thread rolling die, and they're going to be spinning with that 75 horsepower force. This shaft is going to be fed in, and it's going to start to form the threads into it. So let's skip ahead where we see some of it happening. So the oil that's coming out of these orange nozzles is for lubrication, because this does produce a lot of heat. It should start closing down on it. It's a little hard to see, but you can actually see this side is rolling and moving. The other side is too, so they're moving in unison. And you can see it starts to form the threads. Now the threads on these rolling dies are actually ground at an angle so that there's less thread here and more thread out here. On a much smaller scale, this is the more common method of thread forming nowadays because it's very quick. It produces no materials that you need to get rid of. It can be done all within a second on smaller bolts. Same process, but obviously a lot smaller rolling die. Okay, so there's that one. It's just a very powerful machine. All right, so our different threading tools. In the picture here, we've got the first ones, and these are really what a technician should have at minimum, because these are thread repair taps. They are really good at fixing holes that still have usable thread. They don't cut new threads. And you can see on the end of them they have hexes built in, so they're easy to either use a wrench or a socket and put it on a drill. So they're really good at fixing threads. They really form the thread back into shape more than cut it. So they'll remove debris from the hole, from the threaded hole, and then they'll also form the thread hopefully back to a usable shape. So the other types of threads is the taper, plug, and bottoming tap, and I've got those right here. Let me back this out. So this is a tap set that you can purchase. Let's say there's a size that you do a lot, and this here happens to be the 12 millimeter by 1.25. And we see that if we put these in that order, there we go, we have different lengths. So we'll do it here, and then we'll also do it on the PowerPoint. Scooch them over one. Focus. There we go. So we look at these and we see there's this shiny section. This is a ground down section of the tap. And then this one's got a little bit less ground down. And this one has the least amount ground down. So this first one right here is what's called a tapered tap. This tapered tap is very easy to start by hand because you want to make sure that the tapped hole is perpendicular to the surface that it's going into. So this taper tap is the easiest to get a start on. Then we have a plug tap. This tap here is good to continue this one. Let's say we start it, but we need to have it tapped closer to the bottom of the hole. Then we can use a plug tap. The plug tap you can also start by hand. It does tend to be a little bit more difficult, but not much, because it still does have a pretty good taper to help center you on the hole. Now this last one is a bottoming tap, and that should give you a hint as to its function and what the limitations are with these two here. So a bottoming tap is able to cut to the bottom of a hole, let's say it's a blind hole, and it's able to form about 3 threads up from there. So it means maybe 2 to 3 threads at the bottom of the hole will not be usable by the bolt. So we get to the plug tap. This one can form down to 3 threads. This one can form usually down to about 5 threads. And then of course the taper tap is usually about 7 threads. So this one is not good if you need to tap to the bottom of a blind hole. But if you had a through hole, let's say it goes through a block, goes through a bracket or something, this one would be perfectly fine because you could feed it all the way through and then bring it all the way back out. And the bottoming tap is best for blind holes. So up here on the PowerPoint again, we've got another view. So our bottoming tap, we can see that it's usually about 2 to 3 threads that are not fully formed, meaning they can't cut a thread. And then we have a plug tap. We've got about 5 threads, and then the taper tap is usually about 7 threads. And that's their purpose. So taper tap is best to start by hand because it's such a long taper. It'll help center you on the hole. And then on the other end of the spectrum is the bottoming tap. So the other types of taps that we have, and you saw them in the pictures or in the videos, were these two right here, where we have what's called a spiral point tap. So this one here, notice the thread cutting angle is starting up. It's going at this angle there. And that's going to force the chips down to the bottom of the hole. And then we have this spiral flute tap, where the thread cutting angles are actually they're tilted the other way. So that tilt the other way is going to force the cuts or the chips up through to the top of the hole. And these are both for automation. You can cut by hand with them, but they do tend to be difficult to get started. All right, so talking about die, here's a die. This one is really for repairing threads, not so much for cutting straight shafts for threads. They will do it. This one, see, it's hexagonal. If you have one that's a round die, that's usually for cutting shafts with no threads on them at all. So there are round ones and there are hexagonal ones. The ones that we want to use the most or own are going to be the hexagonal ones. And those are the most accessible. So yeah, let's move on to the next one. All right, so we have tap turning tools. There's also a die tool. And back out. Notice these are the two tools that we use to turn taps. Got this guy, which might not fit in there. I don't know if I grabbed the right one. No, I don't think it did. Oh well, I'll just stick one in here. Now, I've got this tap mounted into this tap handle, and this tap can also be mounted in a tap handle like this. Notice that these tap handles are T-handles, so we have, two-sided handles to them, and that's so that you can produce, ideally, pure rotational torque down onto the tap. If we were to do this with a ratchet, well, ratchets don't just put rotational force in, they actually put a bending force. So instead of just trying to twist this guy, they actually try to bend it because we're pulling just on one side of it. Now in using a T-handle like this, the opposing forces, the bending forces that exist will be opposite of each other, and that cancels them out, which hopefully just puts all the torque into twisting the tap. Now the tap itself, they are very strong in that torsional direction, or in the twisting direction. They are not very strong in bending. So if you use a ratchet and you do it wrong, then you will break a tap. And a broken tap is not a good thing because these are oftentimes harder than drill bits, and you need to get a different type of drill bit to get it out. The process for cutting or for threading a new hole. So threading a new hole, we need to access some information. And the first thing is what size hole do we need to drill for a specific hole, or for specific thread, sorry. If we're trying to do, let's say, a 12 by 1.25, like these taps that I have here, okay, we need to know what size hole I got to drill. Okay, and you can use a drill tap chart. Drill tap charts are available. If you just Google it, you'll get numerous hits on that. They're easy to get a hold of, and you just take a look at. And what it's going to do is say, okay, you want to do a 12 by 1.25. This is the size of drill bit you need to drill. You can't just guess. I mean, you can, but it's best to just go ahead and follow a drill tap chart. Let's say you don't have access to a drill tap chart. What you can do is take 75% of the thread diameter, and that's the drill bit you're usually going to go with. But that's not a guess, that's a calculation. Now on this tap, this is our 12 by 1.25. Let's see if I can get that in the shot there. There we go. It's 12 by 1.25 right here. And if we look just underneath that, bring that into view, it says 27/64. So to get a hole 12 by 1.25, this tap is telling you what drill bit to use. Hey, I like that. That's pretty simple. So you need to identify what drill to use. Next thing you want to do is before you drill, you got to center punch it. So you're going to put a divot in that metal because that divot is where the drill bit is going to lie. It's where it's going to follow the hole on. If you try to drill just a flat surface, the drill bit's just going to dance around that surface, and that's all you're going to get out of it. Just get some dancing. So once you center punch it, then you're going to drill it. And you're going to try and drill the hole to depth. If you need a hole to be 10 or say 15 millimeters deep, that's how much thread you need. You have to drill it more than that because remember, taps can't tap to the bottom of the hole, so you need to drill plus some. And then you're going to use the T-handle and slowly advance the tap into the hole. And you're going to reverse the tap. So you're going to turn the tap one turn and then back it off a quarter turn. Go another turn, back it off a quarter turn. And what that backing off is doing is breaking the chips that are getting stuck inside the flutes of the tap. If you don't do that, you break a tap. So here's an example of a drill tap chart. It's kind of a, if you're watching this on your phone, you can't read a damn thing, but this drill tap chart not only does, it shows drill bit sizes, it shows decimal equivalents for those drill bit sizes, and then it also has a tap section. But these blue pieces here, or blue sections are, let's say for, I can have a hard time reading this too. All right, so we got one right here. This guy is for a 7/16-14 threaded hole. It's telling you to use a .368 drill bit or a letter U drill bit. And there you go, you got it. It's a drill tap chart. On the metric side over here, it's all basically just this one section here just for metric. So if we needed to do a 12 by 1.25, it's telling us to use an 8.7 millimeter drill bit, which comes out to 0.3425 inches. So you can figure out what you need by using a drill tap chart or look on the tap. So why threads fail? Well, over torquing. You over torque the fastener. You're not supposed to hurt the threads, but you could have hurt the threads. Remember, if you over torque a fastener, the bolt should break, not the threads. Of course, unless it's a screw, just, you know, maybe it's a close to an A-class fit and you tighten it too much, you could strip it. Cross-threading of the fastener. This one here, in some applications, cross-threading is going to happen. If you cross-thread it, you got to stop. That means that that bolt is not going straight in the hole, it's going off at an angle, and it's not going to fix itself. Incorrect thread length, if you either have too much or too little thread engaged, that will cause a fastener to fail. Contamination, yeah, that's not good either. If you have metal chips or sand or, you know, something that's not supposed to be in the hole, that could cause the threads to fail. And then this last one is hydraulic action. So this one here, let me draw a bolt hole. There we go. And we got this one over here. So these are the, I was doing good on one side. There we go. There's my threaded hole. And let's say this threaded hole has got some liquid in it. Change my pen color. Let's give it some green. It's got coolant down inside it. Or whatever color. I guess that was gray, sorry. So all this stuff down here is a liquid. And we go to try and screw a bolt into this thing. Because these threads produce some sealing effect, you're going to be compressing this stuff. And we know that liquids are it's very difficult to compress them very far. And what you can do in this case is strip out these threads. So, boom, you screwed them because you left coolant in the hole. Or what you could do is, let's say this is a casting. And this casting, go back to my red, let's say this casting goes like this. I have seen this stuff make its way through the casting and then splurt out over here because it found a weak link. And that's damaged the hole and it's possibly damaged the casting. I've even seen this done with silicone. If somebody uses an excessive amount of silicone gets in the hole, they screw the bolt in, boom, they blow off the side of the casting. So you don't ever want to do that. That's not good. And then we're going to stop on this one. So these are the different thread repairs that are available. I'm going to go over each one of them in a separate video. So if you do mess up threads, your first option might be to, oversize the thread. This is, in a lot of cases, just not going to be possible because you might have to go from a 6mm to an 8, and there's not enough thread engagement, so that would require you to go from a 6 to a 10, and there may not be enough material around it to even do that. So in the pictures here, there are 3 different types. We have our helicoil, so this is our helicoil here. Our time inserts, which are over here, and then a solid thread insert, or also called a key insert, to fix a threaded hole that you or I'm sure somebody else has messed up. But like I said, we'll go over each one of these in more detail and the process for the helicoil and the time insert. So until then, I'll see you later.